Welcome, learners. My name, once again, is Mr. Paul Chilola, your teacher. We meet now to revise the 2026 paper from SEED. This is the mock paper, physics paper, practical, which is paper 2. All right, we are going to dwell on questions 1 and 2 only, which are the descriptive questions. So welcome once again. In case you are watching us on our YouTube channel, consider subscribing to the channel so that you get our exam focused content to help you master practical skills and other skills too. It is only on this platform where you get high yield revision that will help you to produce the best results. We are premised on the fact that we have smart revisions to help you practice well and score highly in your MSCE exams. Welcome, learners. My name is Mr. Paul Chilola. Let me call upon you to pay strict attention to the tips, important tips for answering descriptive questions. Remember that for you to get a distinction in physics, you should do well in both papers, paper 1 and paper 2. So in paper 2, you have to get 10 out of 10 per question in all the 10 questions. This is 40 marks. That means you have to score 10 marks in each question. So we'll guide you. How do you make sure that you score 10 out of 10 per question? Welcome, learners. Invite your friends, wherever they may be, to join us so that they too can benefit from our high yield revisions. So without wasting your precious time, let us proceed to look at question number 1. Is asking us to use a well-labeled diagram to describe an experiment that can be done to verify Hooke's law. Hooke's law. All right, so the examiner is assuming already that you know what Hooke's law states. Because unless you know what Hooke's law states, it will be difficult for you to describe this question, to describe this experiment. All right, so what does Hooke's law state? Recall that Hooke's law has to do with springs and the materials in general. It states that the extension of the spring is directly proportional to the load on it, provided the spring does not get damaged, provided the spring is within what is called the elastic limit. As long as the elastic limit is not exceeded, the extension, which is the increase in length of the spring, is directly proportional to the force or to the load on the spring. Remember that load refers to weight of an object which is hooked or attached to the spring. So according to Hooke's law, the higher the load on the spring, the greater would be the extension or increase in length. So we are asked to use a diagram, well-labeled diagram, to describe this experiment, to verify Hooke's law. To verify simply means to prove that indeed, to confirm that indeed Hooke's law is a valid law, it's valid. So what experiment can you carry out? We can do that. We can describe the experiment by use of a well-labeled diagram. Well-labeled diagram. So such a diagram will look like this. Such a diagram will look like this. All right, so the diagram that is required here is this one, shown here. It's the one that you are supposed to draw, or the candidates who are writing this exam were supposed to produce this diagram. Very, very important. So, your examiners shall require you to draw the diagram as neatly as possible. Draw the diagram as neatly as you can using a pencil. Don't use ink when drawing this diagram or any other diagram in an exam. Use pencil. So you use pencil to draw the diagram, but you can label using ink. The labels can be in ink, but the diagram should be drawn in pencil. Take note of that. This is what many candidates would forget. So as you're entering the exam, make sure you have an HB pencil to draw diagrams with. So draw a diagram as neatly as possible. Don't draw a shaded diagram, a sloped diagram. Sloped diagrams are boring when it comes to marking them. They're boring and awkward. If you draw a bad diagram, what's going to happen is that it will actually develop a negative attitude in the examiner. And as a result, the examiner will not mark your question as effectively as possible. All right, there's going to be a problem marking such a diagram. Make sure that your diagram is super neat. Draw a diagram which is super neat. Don't be sloppy. Draw as accurately as possible using pencil, but when you putting the labels, the words, these words, use ink. So all these lines must be drawn in pencil. So when you have drawn your diagram accurately, just by drawing an accurate diagram, you already have got 1 mark for drawing an accurate setup for diagram, 1 mark. And by labeling at least 3 parts, you have 2 marks. So altogether you have 3 marks for the diagram. So you have a spring here, you need a spring, you need a clamp to which the spring is hung, and you also need a stand to support your setup. And you will need a mass hooked to the diagram, to the spring. When labeling this diagram, we'll forget to label the ruler. So that's the ruler. That's the ruler. Welcome, learners. So having drawn a correct diagram, now you have to refer to it. Whatever you say down here must make a reference to the diagram. Now you are describing how you can verify the Hooke's law, how the diagram can be used to verify Hooke's law. So whatever you are saying down here, you have to refer to the diagram. So you proceed by saying, set up the apparatus as shown above. So you are referring to the diagram that you just drew, right? So this is the setup, okay? So make sure whatever you are saying down here is making a reference to the diagram there. Do not give a description that does not speak to the diagram. Right? Then measure the initial length of the spring. Measure the initial length of the spring under 0 mass, meaning that before a mass is hung there,
No, it's okay. They're ready. Yeah, now everything's okay.
Okay. It's in there.
All the papers are with me.
They're with him.
I've taken them.
They're with you.
Yeah, can I put them in?
Yes, please.
It's safer.
Yeah.
Yeah.
Okay, sir. So measure the length of the spring under 0 mass. Meaning the length of the spring before mass is hung here Using a meter ruler, measure the initial length. Initial means the first length before a mass is hung there. So measure the initial length of the spring under zero mass, meaning that before mass is hung there. Then you add 100-gram mass to the spring, this mass here, to the spring attached to the clamp. Add 100 grams mass to the spring attached to the clamp. All right. So having added mass there, it means you see a change in the length of the spring. The spring is going to elongate. It's going to elongate or increase in length. So in this case, you have two lengths. One length is before mass is hung here. The other length is when the mass is hung on this one. So you record the new length of the spring using the meter ruler, which you have just measured. Record the new length of the spring. The new length of the spring is one that is produced by the mass. The mass being hung there will cause the spring to increase in length. So that's the new length. The initial length is one you measured before a mass is attached to the spring. The new length is the one that is due to the mass being hung there. This is going to stretch down, further down, to give you a new length. Using these two lengths, now you can find the extension. Find the extension of the spring by subtracting the initial length of the spring from the final length of the spring. The final length minus the initial length will give us extension. Extension is simply the increase in length or the change in length. So the increase in length can be found by subtracting the initial length from the final length. That will give you the extension. So you do the same. You repeat steps C, D, and E with different masses. In this case, 150 grams, 200 grams, 250 grams, and 300 grams, and record the results in a table of results, appropriate table of results. So for each mass, you calculate and record the extension of the spring in the table of results. Calculate and record extension of the spring in the table of results. So your table will show the masses starting with 100 grams, 150 grams, 250 grams, up to 300 in a column. And for each mass, you have another column to show the new length. And then the other column is going to show extension. Extension is obtained by subtracting the new length minus the initial length. So you have data now which you can use to plot a graph. So plot the graph of extension against applied force. The applied force is simply the weight of these masses. Okay, so in another column, you will have the weights, these converted to weights. If you are doing this practically in a practical. Thank you, sir.
This is someone is playing that was like
A student?
I think so, because it's now enrolled.
Oh.
They are writing maths
Now.
Now, and then they will write history.
Yes.
After that, then after break, geography.
So after break, geography.
Yes, now I'm there.
Okay.
You went what?
Yes, sir. Thank you, sir. So plot the graph of extension against applied force. The applied force here is not the masses. The applied force is going to be these masses changed to newtons. Let's see, if you are doing this practically, you'll need to change these to force or weight in newtons. So this is 1.5 newtons. This is 2 newtons. This is 2.5 newtons. Up to 3 newtons. But don't convert these in this description. We are just looking at a situation where you are doing this practically. Your table of values will have to include the weights too in newtons. So these are newtons. The 100 grams mass is 1 newton, this one. You will need these newtons, these weights, if you are doing the actual practical experiment. Remember, here we are just describing the experiment that can be done to show, to verify Hooke's law. So these are the descriptions. Don't worry about these numbers, the 1.5. In this description, you don't need these. Just proceed to say plot a graph, plot the graph of extension against applied force. Plot the graph of extension against the applied force. So once you plot the graph, it is the nature of the graph that is going to guide you to make a valid conclusion regarding Hooke's law. So you conclude by saying that if the graph is a straight line through the origin, then the extension of the spring is directly proportional to the load on the spring, provided the limit of proportionality is not exceeded. So this is what Hooke's law says. So this is the conclusion. So according to Hooke's law, when you plot the values of extension against force applied, the graph line must be a straight line. That's as long as the spring is not damaged. In other words, provided the spring, the limit of proportionality is not exceeded. Welcome, learners. So this is what the candidates were expected to say. So let's see the allocation of marks. So for the diagram, correct diagram, 1 mark. For correct diagram, 2 marks for the label. So together here, you have 3 marks. 3 marks for the diagram. All right. By saying measure the initial length of the spring under the zero mass, so measure what? The spring, the initial length, 1 mark. When there's no mass on it, another mark. Add the 100 grams mass to the spring attached. Okay, we can give this 1 mark. This instruction, all of it, 1 mark. Remember, the total mark is 10. So this is 1 mark. By saying add 100 grams mass to the spring attached to the clamp, add mass, that's 1 mark again. Then record the new length of the spring, that's 1 mark. Find the extension of the spring by subtracting the initial length of the spring from the final. Find extension, 1 mark. Repeat the steps C to E for masses 150, 200, 250, 300 grams. That's 1 mark. Calculate and record the extension of the spring in the table of results. So for each mass you calculate extension. This is again 1 mark. Then plot the graph of the extension versus applied force. That's 1 mark. Then the conclusion, if the graph is a straight line through the origin, then the extension of the spring is directly proportional to the load. By saying that if the graph is straight line, through the origin, that's 1 mark, then the extension of the spring is directly proportional to the load on the spring, provided the limit of proportionality is not exceeded. Again, that's 1 mark. So altogether you have 3 marks there for the diagram. 4, 5, 6, 7, 8, 9, 10, 11. So we have too many marks. See? We can give the diagram. If we give the diagram 2 marks, 1 mark for the correct diagram, and 1 mark for the labels. So we have 2 marks there. Then it's 3 marks for saying measure the initial length. 3, then 4, 5. Let's see. Let's make sure that we don't over allocate marks. So we have 2 for the diagram. 3, 4, 5, 6, 7, 8, 9, 10. All right, we have too many marks. So the last point, we can just give it 1. Give it 1 mark so that we have a total of 1 or 10 marks altogether. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you have done all these and you have satisfied the requirements of the question, you should be able to get 10 out of 10. Welcome, learners. My name once again is Mr. Pochilola, your teacher. Consider subscribing to our YouTube channel so that every time we upload a new video lesson, you are notified on time. Welcome to question number 2. Question number 2 is asking us to describe an experiment We are being asked to describe an experiment to show that sound cannot travel in a vacuum. Remember that a vacuum is an empty space which does not contain any particles. Space that does not contain any particles, space that does not contain any solids, whether gaseous or solid particles, such a space is called vacuum. So we are asked to describe an experiment that we can do to show that sound does not travel in a vacuum. Remember that for sound to be produced, there is need for particles to vibrate. And in the absence of such vibrations, sound cannot be produced. All right? There must be matter to transmit the vibrations, to transmit the sound. Sound can travel through particles, gases, through liquids and solids, but not in a vacuum. So how can we show that experimentally? One thing I need to point out is that this question does not ask us to use a diagram. When a question is silent about diagram, don't go ahead to draw one. It means you are violating the requirements of the question. If the question is quiet, is silent about diagram, don't draw one. All right, so for this one, we are just asked to describe the experiment without diagram. But you can have a picture as to what diagram you would need. Let's suppose that the question was asking you to use a diagram. Then the diagram you would need is something like this. Although the question is silent about diagram, you can sketch this somewhere on one of your rough papers if you have in the exam. Just sketch this to help you describe. That's what I would also do. Sketch this somewhere, not as part of the answer, but just somewhere to help me describe this experiment. So if the question is said, with the aid of a well-labeled diagram, this is the diagram that we would draw. So sketch it somewhere and then use it to describe, but don't draw it as part of an answer. Take note, don't draw it in the paper here. Draw it somewhere on a rough paper if you have. Sometimes you're going to have extra answer sheets. That's where you're going to scribble this. Or you can also just find some at the very back of your paper there. You can find space where you can sketch this just to help you in describing this experiment. But don't draw it as part of the answer here, because the question has not said we should use a diagram. So in describing this experiment, so you have this diagram at the back of your mind. You begin by saying, place the electric bell. While you are looking at your rough diagram, place the electric bell. This is the electric bell in a bell jar. The bell jar is this container here outside. Place the electric bell in a bell jar. That's how it begins. That's 1 mark already. I've started making marks, 1 mark, by just saying this. Next, you go ahead to say, switch on the electric bell and observe what happens. So you are still referring to your sketch diagram. Switch on the electric bell and observe what happens, if the sound is heard or not. And record the results in the table of results. So 1 mark for saying place the electric bell in a bell jar. Switch on the electric bell and observe what happens. And record the results in the table of results. Next, you say pump the air out of the bell jar gradually, meaning slowly, to remove the air from the bell jar. That means you are creating a vacuum now. You're creating a vacuum by sucking out air, pumping out air from the bell, from the jar here. Initially, there is air there, all right? Okay. Now you pump the air out, observe what happens. What is happening to the intensity of the sound? You are now observing the amount of sound. As the air is being removed, what is going to be happening in relation to the intensity of sound? And observe what happens when all the air has been pumped out of the bell jar, and record the results as is shown in the table here. So you sketch the table like this, table of results, just sketch, right? Draw one, you can draw one, yes, but don't fill up this part because you are just describing the experiment. You have not yet made a conclusion based on your observations, so you are just describing the experiment, so there will be no need to fill up these spaces unless you are actually doing the practical yourself. All right. This is just sketch of the table that you need to use. In the conclusion there, you have to state by giving a condition. If sound is heard when there's air in the bell and is not heard when there's no air in the bell, it means that sound cannot travel in a vacuum. So this is how you do present your answer. Remember that the question did not specify, did not spell out whether we need a diagram or not. So when there's no mention of diagram, don't draw one. I repeat that. Don't draw a diagram when the question is silent about a diagram. So this is what you are supposed to have said if you are to write this exam yourself. So let's allocate marks. Placing the electric bell in the jar, 1 mark. Switch on the electric bell and observe what happens. By saying switch on the electric bell, that's 1 mark. And observe, 1 mark. Pump the air out of the bell jar gradually, 1 mark. And observe what happens, 1 mark again. Then observe what happens when air is completely out of the bell, is removed. 1 mark. Record the results in a table, 1 mark. So you have, so far you have 1, 2, 3, 4, 5, 6, 7. 7. Since we have already referred to the table here, you may not gain marks for saying this, but it is just adding value to your response above. If sound is heard when there is air in the bell jar and is not heard when there is no air in the bell jar. If sound is heard when there is air in the bell jar and is not heard when there is no air in the bell jar, that's 1 mark. Then it means that sound cannot travel in a vacuum. That's another mark. So don't make a conclusion that says it will be observed that when air is removed from the bell jar, sound is not heard. No, don't say that it will be observed that sound will be heard when air is. Okay, what I'm saying is, avoid saying it will be observed that. Such conclusions are not acceptable. All right? Your conclusion must start with if. If sound is heard when there is air in the bell jar and is not heard when there is no air in the bell jar. That's how you conclude your descriptive essays, unless you are being asked to describe how you can prepare something, or unless you are asked to describe how something works. That's different. But where you are looking at the effects, the cause-effect relationship, you should end your conclusion by saying, if this, then that. Even the previous question, we said, if the line is straight, the graph line is straight, then it means that Hooke's law is verified. So be careful there when concluding. So once again, this is a 10 marks question. Let's verify. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 marks altogether. Welcome, learners. So that's all we can say for this paper. In case you have questions, don't hesitate to send me a text message to WhatsApp, my WhatsApp number. I'm sure you have found so far you know my number from the other videos. Of course, in this video, I've not given the number, but the other videos are spelling out the number very well for you to send your inquiries, questions, how you can enroll into our classrooms. Welcome, learners. For the time being, I wish you all the best, expecting to meet you again. Keep revising, keep pushing. I trust in you. Hard work, your hard work will pay. Your hard work will pay you. Bye-bye for now.